HyperLynx DRC will read in board data from any layout system and allow you to perform electrical rule checking on the board through a series of design rule checks, or DRCs. All of the built-in DRCs contain a series of parameters that allow you to adjust the rule to meet the needs of your specific design. This particular DRC, Nets Crossing Gaps, is concerned with traces going over gaps or splits in the reference plane. And some of the parameters that you can set are the size of holes that a trace might go over, which reference planes are active or to be considered reference planes in the analysis. And then when the DRC completes, all of the violations, when you click on them, will turn on and off the appropriate layers to allow you to view the violation more easily. And there's also a series of actions to the right that you can also do that automatically occur as well. But each of these violations, as you click on them, allow you to see the violation very clearly where it is on the board. Another popular EMI DRC is the vertical reference plane change, and this one is concerned with signal vias that are routed without a surrounding stitching via or stitching capacitor. So some of the parameters that you can set are the distance to a decoupling capacitor or stitching via, as well as, like Nets Crossing Gaps, which planes are to be considered reference planes during the check. And again, as you click through the violations, you can see very clearly where the violation is, the search radius around the violation, and be able to take corrective action as a result of that. Now, some of the built-in DRCs actually use the field solver. So this differential impedance check will go through and actually check the differential impedance along all the different sections of a differential trace pair. So if we go through the different violations here, we can find things that, some of which you might be able to see visually by reviewing the board manually, but some might be a little harder to spot. And so being able to actually calculate the differential impedance is very helpful in allowing you to find these violations. Like for instance, on this differential trace pair, you can see where it's breaking apart, pretty obvious violation of the differential impedance, but this diagonal section might not be intuitive to find that kind of violation. Now, in addition to all the built-in DRCs, you can also write custom DRCs to automate the manual checks that you perform on a board design now. For instance, this decoupling coverage check is a very simple check that just looks for power pins to make sure that there's a certain amount of decoupling capacitor coverage for each power pin. So it's looking for decoupling capacitors within a certain search radius. Much simpler than doing a full decoupling analysis, but it's a good first pass at finding issues. This proximity check DRC, another custom DRC that we wrote, basically searches for high voltage nets and make sure that there's no metal within a certain safe distance. So in the X, Y, and Z directions, it will ensure that no metal is within a certain distance of a high voltage net. And if we go through the violations, we can see where it's found metal within our safe distance, which in this case was 50 mils. So basically, you can use HyperLynx DRC to check for anything that you might otherwise manually check for on the board, and also items which aren't easily simulatable, like EMI problems. In addition to doing checks before you run a simulation, like just looking at impedances to make sure that they met your specifications.